Hey guys, it's me, Nate. So today we're going to be talking about some tips and tricks that you can incorporate in your robot to help with the performance and the consistency in your programs. Also, we'll be talking about performance and consistency on the competition board, because there's nothing worse than getting to the competition and then your programs don't work and you don't know how to fix them. So we'll be talking about some mechanical changes incorporated in your robot, and then also some software changes. So we'll be using my team's robot today, Technobot's robot, and we'll be talking about how we incorporated some of those features into our robot when building it. Alright, so today's lesson is mainly going to be split into three main sections: robot tips, ways that your team can use to save time, and programming tips. So we'll be splitting these sections into micro sections, so mini bullets, and talking about some tips individually in each section. So robot tips, we have a couple different ways. Ways to save time, we have multiple different versions. And programming tips, we have a couple programming features you can incorporate in your code, so then you can get some consistency out of that. All right, let's dive right in with the box style robot. All right, so the box style robot is basically like a robot that's, in a sense, the outer shell is a box or a rectangle. So it's basically flat on all sides, and that way has nothing sticking out of the sides of the robot or the front or back. And that prevents it from being caught on anything. Like if a wire was sticking out, it might get caught on a wire, like a mission might get tangled in the wire and then your robot fails. Or if you have just an arm sticking out or something like that permanently, then an attachment might get caught on a mission while trying to drive past it, and then your robot will also fail. So let's talk about how our robot incorporates this feature. So you can see we use these rectangular blocks on all sides of the robot. This side's pretty flat. You can see that this side's also flat. The side on the back's flat. And we actually use a Lego rubber band there to hold our cable, so then that doesn't push out the back of the robot. Our cables are tucked inside the robot. And then on the left side, you can see that that's also flat. Alright, so let's talk about the next section. And the next section is attachment. Alright, so I got two motors here for attachment purposes, so we can demonstrate some things. One of them can have, it's a little bit slow when it comes to attachments. The other one's a little bit faster. So let's talk about the basic change that can make things a lot faster for your team. So this is what newer teams typically have set up on their robot, where if they want to switch an attachment, they pull this entire axle out of the motor, and then they put their attachment, and then they just feed their new attachment back into the motor. Like that, and then they're good to go. However, this is a problem because you can save a lot more time than having to manually reach in there, especially if your motors are in a bad place, like they're not very accessible. That can take a lot of time, or sometimes reaching your hands in there under stress and competition for the students. They might accidentally break something on the robot, and then that's even worse. So this is a way you can incorporate quicker attachments that's very simple. So all you have to do is add axle extenders on either side of your motors. That also extends to the point where you attach your attachments, which may help with accessibility possibly. So all you have to do to remove your attachment on your arm is you just clip it in and clip it out. It's that simple. It's very accessible, and it's a lot easier and faster to use. You can actually get pretty quick attachments on. My team used this 2 years ago for our attachments, and it helped us drastically from the year before, where we were just manually connecting each attachment together. So the next point is building structurally sound. So here's one of our jigs that we use for our robot in competition. You can see that it's built in a box formation. That way, in a box, it's really strong. That's also why a lot of teams build their robot in the box, also the box style robot, because it's strong on all sides, and it's less likely to break if dropped or something like that. Because let's be honest, we all make mistakes sometimes, and sometimes the students do accidentally drop the attachment or drop the robot even. And you want to make sure that it doesn't shatter at competition if that were the case. So you can even see with our robot, we build everything structurally sound. So I work with the students, and I do some classes with them in the off season to teach them about building things very strong. So you can see even if I drop our robot from this, it didn't break at all. The robot's just, it's fine, and it's ready to go back down and drive around. So you don't want it to shatter. Otherwise, if it happens at competition, you can be in a really big mess. So let's talk about sensor use on the robot, because that's the next point. So sensors can really make or break your robot. If you can do them correctly, they can really make your robot unique and make it work really well and efficiently. But if you use sensors incorrectly, you can get a big mess at competition. That's really difficult, and they can end up making your robot worse than it would be without sensors. So here's our robot. You can see on the bottom we have 3 color sensors, one on the left, middle, and right, mainly because we use color sensors all the time. That's the sensor we use most on my team, and so we would like, the flexibility of being able to follow a line on the left side of the robot, the right side of the robot, or in the middle of the robot. So that's why we have 3 of them scattered across the front. We've actually had 3 of them on the front of our robot for about 4 years now, actually, and we've really enjoyed it, and that's why we keep it every year. So our last sensor, which is the 4th one, that is a gyro sensor right here. So that's plugged in. Here, let me pull it out for you real quick. You can see the gyro sensor. So the gyro sensor measures your angle of your robot, and it measures like specifically angles. So like if you want to turn, say 45 degrees, you can use a gyro sensor to turn 45 degrees. However, we mainly use it for just driving forward straight. So we try to use it like if our robot has an issue with, I don't know, crossing the field with like a lot of weights on the side of the robot or something. We tend to use our gyro sensor to make it drive straight. Those are the 4 sensors we use. We sometimes do line following, with our color sensors. Sometimes we use the color sensors to do like line tracking. So like when we touch a black line, our robot will stop, or, wave an attachment or something like that. Or sometimes, we even use a gyro sensor to, do some turns, sometimes, depending on the case. But, you can use these sensors in, a bunch of applications. Those are just some of the applications off the top of my head that we use our sensors for. So let's talk about the next point, which is wheel support. So really, you don't have to worry about this point if you have a very small robot, but if you have a bigger robot like my team does, then you probably, you should consider this. Because it could help you. You may not need it, but it could help. So, in our case, where we have, a pretty big robot, it's pretty long. There's a lot of weight on this robot sometimes with the attachments on it, because the attachments are pretty big sometimes. So, if your wheels flex, because, like your axles on the outside of the wheels, because, with all the weight, if your wheels end up flexing, then that's not a good thing. Your robot will have some problems with consistency. So we actually add support on the outside of our wheels. You can see that here's the wheel on the inside, and then you can see this little thing, which our axle runs through. If I turn it, you should be able to see it turning. So we do that on both sides of our robot. We add some outside support on the robot wheels, and that way, our axles are less prone to flexing, and thus we get a little bit more consistency in our programs than you would without it. Alright guys, so let's talk about some ways that your team can use to save some time. So let's talk about attachments. So I mentioned the attachments earlier. If you can speed those up, then you can have some more time to score some points on the field, which will benefit your team overall. Typically, newer teams spend upwards of an entire minute switching attachments. When you only have 2 minutes and 30 seconds to drive around the field and score points, a whole minute of attachments, that can really affect your performance and robot points overall. So you want to try to get your attachments as fast as possible. That way you optimize the time your robot's driving around the field and scoring. Consistency and precision is very important. You want your robot to be consistent and do the same motions on the board, but you also want it to be precise in the sense that it scores the mission every time. So you want to make sure that your robot, especially on your practice field, is scoring consistency and precision about 80% to 90% of the time. Because you can expect that when you get to competition with the board variability, which we'll talk about next, the boards are going to be a little bit different, and your consistency is going to drop a tiny bit. So let's talk about adapting to variability. So like I mentioned, the boards are a little bit different at competition. Well, how are they different? Well, on the edges of your board, depending on how the dimensions that you built your board to, that first gives you, if it's a tight fit or maybe it's a loose fit. Typically, our board is actually a very tight fit. Our field, our mat goes around the edges of the field or the board itself, and it's pretty tight against the walls of the field. So, though when we get to competitions, a lot of times there's a big gap between the mat and the wall. That's because, you can expect a little bit of variability with the people that build the boards. Sometimes, a person built to, say, like a 1/4 inch bigger than they should have, and unfortunately, you just have to learn to work with that kind of variability on the field. So it's good to make sure, have your kids test coding on the fly, like changes like that. Make sure your robot's able to make changes like that on the fly, because you can expect them. When you get to competition, you're really going to need to change your robot and tune it to that playing field. So usually if you ask, the staff and the referees, you're allowed to go up to the official match playing fields beforehand, and ask them that you can view them. Usually they let you walk up and take a look at them, just, so you can get an understanding of what those kind of boards look like. How big is the space between the wall and the mat? That's very important. There's nothing worse than getting on, expecting 80% consistency from your home field, going to competition, and then competing on the field in match 1, and then realizing that you only got like 10% of your points that you were supposed to get. So that's a pretty big deal. So make sure you have your variability set out, and that your kids are used to making changes on the fly. So let's talk about speed and practice time. So speed, that kind of goes along with consistency on your robot. Let's say you're running 80% speed, but your mission's only 50% consistent. So you might want to consider dropping your speed to, say, 60%. If it makes it that your program is now 80% consistent at 60% speed, then you should consider permanently changing your speed to 60%. Because I would say that if you only have a 50% consistency, try to get it a little more consistent, because that means that you might have to run it 2 times in one of the matches to get the points from it, and that's not good. You should only have to run your mission 1 time. Or I apologize, you should only have to run your program 1 time to score the missions. So practice. So we typically start practicing, I start practicing with my team, having them practice attachments about 3 weeks in advance of the competition. Because normally, like the first time we practice, our attachments in a full 2.5 minute run, we will usually get, we've had upwards of 8 minutes that, the first time we've practiced. And everyone's, looking at themselves like, oh no, how are we supposed to score all these points that we just, in 2.5 minutes when we just ran through it and it took us 8 minutes to score the points? Well, that's where practice comes in. Last year, for example, we were taking 8 minutes on the first time we ran our programs through a 2.5 minute run. We took 8 minutes to score all the points that we had planned. However, by the time competition came around, with practicing every day with the students and them getting used to the styles that the other students have when doing attachments and working together, they were actually able to fit it in 2.5 minutes. So practice. When you get to competition and the kids are on the field getting ready to run match 1, that should not be the first time they've practiced 2.5 minutes. So let's move into the programming tips. Let's talk about some software and programming tips you can use to get some more consistent programs. Alright, I don't need to update that right now. Alright, so you can see I've connected to our robot right now. If you go into this this port view slot right here, you can actually see all your your motors, and then you can also see all your sensors down here and the values that they're having. So let's start with sensors. So the sensors, like I said, we use 3 color sensors and a gyro, but I'll talk about sensors as a whole. So using sensors can make or break your robot performance, like I mentioned earlier. The reason being, if you use sensors incorrectly, you can have a headache, where you don't know what's going on, and your robot's just acting really crazy, and it's not, you thought that sensors would help with your performance, but it's actually making it much worse. So I would recommend, getting a little bit familiar with the sensors before you dive right into, trying to code them. Maybe take some tutorials online. I have some tutorials on my channel if you're interested in them. Get a little bit familiar with the sensors and how they work. That way, you understand them, and if you need to make a coding change on the fly at competition, your students can actually do that for them. They understand the sensors, they know how to make the change. Let's talk about, making changes on the fly. Like I said, your students should be able to make changes on the fly with sensor. If you use sensors, they should be able to make the sensor changes on the fly. Your students should also be able to make general coding changes on the fly. You can actually add coding notes down here if you click this little text box comment option. That way the kids can actually document their code, and it's a lot easier to follow. So let's say I just want to drive forward 3 rotations, right? So they can actually say drive forward from base 3 rotations. And if this is, let's say that, we have all these blocks here. I'm just going to drag a bunch of them, like this. And let's say they, it gets a little mixed up. So let's say they want to know what, this block does, where it's farther in the program. then, you know, it might be worth it to add a note here. Drive forward 1 rotation. You know, after attachment. Because this block's an attachment, so then they know that this block is right after your attachment swings or whatever it does, and you know, they know that this block is right after your attachment. So then they can visualize and know where the change needs to be made in the code. All right, let's also talk about, you know, understanding the code. So you need to make sure that your students understand the code. Also, it's good if you, as you know, a coach, understand the code as well. I know the code fairly fluent, and you know, on the EV3 software. That way, you know, if the students are having some trouble, maybe I can guide them in the right direction, and, you know, give them some pointers, and you know, say, oh, you know, your light sensor is acting a little funny. Maybe look into something like that. That could be your problem. So take a look at your light sensor block. So also, like I said, simplicity always is important. Not just on the robot mechanical design, but also in your code. How do you make your code simple, you say? Well, the first thing is, like I've mentioned many times before, you know, understanding your code. So, you know, if you can understand your code really well, then it's pretty simple to you, and, you know, you can make changes on the fly and stuff like that. If you don't understand it, then it's going to be a lot tougher. Also, you know, you should not have code that you don't think your robot can handle. So make sure that you code things in that your robot can handle. When I say that, I mean like if you drive forward and, like, let's say you drive forward and swinging an attachment at the same time. If your robot's shaking a lot while swinging the attachment, you might not want to be moving while that attachment is swinging, because that could throw off your drive blocks and, you know, the movement of your robot. So make sure you only code what your robot can handle. Like I said, down here you can see the values of your sensors. That actually is a section that my students go to all the time, you know, when diagnosing problems. If a value, here, let me do something for you guys so you can get a look at it. So if something like let's say something like this happens, where, like, sometimes your light will even be on your color sensor, where, like, your light's on your robot, and you're like, oh, well, the sensor has power, but for some reason it's not working. Go to your port view, and if it's out like this, there's no input, that means that your wire's probably pretty loose. So it's best, even if it's turned on, it still could be loose. So it's best to unplug your wire completely, like so, plug it back in, and you should get your value. Yep, there you go, and your value's back. So that means, you know, that can help diagnose some of the sensor issues for you. You know, that can be done in any sensor. It's not just the light sensors that have that kind of issue. You know, if your gyro sensor is not recognized in your software, maybe unplug it, plug it back in. If that still doesn't help, maybe try rebooting your brick, or just replacing your cable, and that should help you. All right, well, I really hope you guys enjoyed this tutorial. If you guys have any questions about how our robot, how our robot does anything, or how our robot, drives along the board or something like that, then feel free to comment in the comments section. If you like these tutorials, please like and subscribe, and also comment. I'll be posting some more tutorials for you guys in the code. That way you guys can get a better understanding and help you guys out with some sensors. All right, until next time.